like to go over with you, just get some more practice with it, and then one or two things to go through in the end when I see you, because I'll be seeing you for the lecture on Friday. So we'll do a few more examples and maybe just look at a few other aspects of the transform before we leave the chapter behind to do the Fourier series chapter from next week. Okay. So what we finished with last week. So we were introducing the Heaviside step function and Dirac delta function and looking at the Laplace transforms of those. And we finished off by working through example 2.13, I think here last Monday. So you can see the recording of that on the Google Plus page and look at the scanned pages are up there also. Okay. So just a couple little of things, just a few little items here. Before we go and look at a past paper example. So in section 2.6 on page 56, well, there's just a couple of technical terms, just some terminology that we sometimes use. These are steady state and transient solutions. So these are just terms that can be applied to parts of a solution. When you have a solution made up of a linear combination of various functions, we can refer to some of them as steady state terms and others as transient. And the terms are fairly descriptive. So for instance, in this ODE here, we're not going to solve, but we'll just look at the solution that it has. So this ODE, the second order ODE in y, d2y dt squared plus 4y equals that exponential plus 8. This is what its solution is here. So y of t is 3 times the cosine of t plus 2 times that exponential e to the minus t plus 2. Now in this solution, the exponential term e to the minus t can be called transient. Okay? Because thinking of t as the time variable, as time goes on, this exponential term here fades away. It converges to 0. Okay, so it's transient. Its effect, while its effect is always there, its effect diminishes over time and goes to 0 over time. So we call that transient. Transient, something that doesn't stick around, so to speak. The other terms, 3 times the cosine and the constant term 2, they can be termed steady state. They represent a kind of steady state part of the solution. They're always around. Now, the cosine, of course, does appear and disappear, because the cosine varies periodically through time. That one would go to a maximum value of 3 and minus 3, but it also fades away as well, but it never fades away completely. You know, it just fades away temporarily. Its effect is always there throughout the lifetime of the solution. Okay? And of course, the constant 2 is always there as a constant 2. So we have this idea of steady state and transient solutions. So sometimes the questions might ask us to classify the various parts or the various terms in the linear combination of the solution and call them either steady state or transient. In section 2.7, we have a couple of theorems here about how limiting values of a function and its transform are related in a couple of ways. Okay, so this is called the initial value and final value theorems. They're referring to the initial value of the Laplace transform and the final value of the Laplace transform. So here we have a situation where we've got a function f, function little f of t with the Laplace transform capital F of s. Now we won't spend time looking at the proofs of these, but the way they'll function for us is as a kind of a consistency check we can perform. So if we've taken the Laplace transform of a complicated looking function, these are some aspects of it that we can check, and if either of these are violated, then we know something has gone wrong along the way, or perhaps we haven't taken the Laplace transform correctly, or we've misapplied some of the standard results about the Laplace transform. So the initial value theorem refers to the limit as s goes to 0 of, well, not of the Laplace transform itself, but of s times the Laplace transform. And this theorem asserts that this limiting value is equal to the limiting value of f, the original function, little f of t, but as t goes to infinity. And secondly, the final value theorem kind of has the limiting variables going in the opposite direction. So this time we're taking the limit as s goes to infinity of s times the Laplace transform of f. And this asserts that this limit is going to be equal to the limiting value of the function f as t goes to 0. Okay. Now, we won't spend time on the proof of those, but we can have a look at them in the case of we can do this example 2.14. We can have a look at this in the case of the function in 2.55. Example 2.14. Okay, so we can just verify that these theorems hold in the case of the function y in 2.55. So that function y is, we have y of t is 3 times the cosine of 2t. It's 2 times the exponential 2 to the minus 2 times e to the minus t plus 2. And so some of these limits that we'll need, we're going to need the limit for the final value theorem. We're going to need the limit as t goes to 0 of y of t. Well, the limit as t goes to 0, all these functions are continuous functions at 0, so we can work out that limit by simply just substituting in the value 0. And when t equals 0, the cosine of 0 is 1, of course. You just get 3. The exponential e to the 0 is 1, so you get 2. Then you get another 2 at the end, so we come up with 7. So 7 is the limit we'll expect to see in the corresponding limit for the transform of S. The other theorem, well, the other theorem about the initial value theorem won't actually be applicable here because the function y doesn't have a limit as t goes to infinity. T goes to infinity, okay, the exponential part fades away, converges to 0. The constant remains at its constant value, but this cosine is just endlessly varying between 3 and minus 3. So the function doesn't have a limit, okay? So actually the initial value theorem won't be applicable, or we should see the similar thing on the other side, that the limit, the corresponding limit of the transform function shouldn't exist either. Now, I need to find we need to take the Laplace transform to look at the corresponding limit of the function y of s. I just have to look at the table to remind myself what these Laplace transforms are. So we got 3 times a cosine. So this transform is 3 times s over s squared plus omega squared, and omega is 2, so it's going to be s squared plus 4. So 3 times s over s squared plus 4. And the exponential e to the minus t goes to 1 over s plus 1. And the constant 2 has the limit 2 over, as the transform, 2 over s. Okay, so this is taking the Laplace transform of the function y using the tables, using standard results in the table. And so we can check the final value theorem. So we can take the limit as s goes to
as s goes to infinity, of s times y of s. Okay. So this will be the limit as s goes to infinity of 3s squared over s squared plus 4 plus 2s over s plus 1 plus 2s over s. The limit of all of this. Well, you can see a few things here. These s's will cancel. And really they kind of cancel in the other cases as well, because as s goes to infinity, the factor adding on 4 and adding on 1 there is becoming less and less significant as s gets larger and larger. But if you wanted to see the evaluation of the limit without kind of hand waving like that, you could say, well, you could divide each of these fractions above and below by an appropriate power of s. So you could divide above and below by s squared here, so this would leave it as 3 times 1 plus 4 over s squared. And divide the second one above and below by s, would leave you 2 over 1 plus 1 over s. And there we can say the s's have cancelled, so this is just reduced to the constant 2. And now you can see, now we can take the limit of this, because the only where we have s here is in this little term 4 over s squared. As s goes to infinity, that of course is going to go to 0, 4 over s squared. And here, 1 plus 1 over s, as s goes to infinity, 1 over s goes to 0 as well. So this limit is just going to be your 3 plus 2 plus 2. So again, we get 7. So we can see this as a kind of a check or a confirmation on the fact that we took the Laplace transform correctly. Okay. So that was the final value theorem. Yeah. So the final value theorem holds here. Okay. It will hold everywhere where the Laplace transform exists and the respective limits exist, so that the equation given by the theorem makes sense at all. Okay, so that's kind of the end of the material in the notes on the Laplace transform. So for the rest of the time this morning, I want to go to another past paper example, and then we'll just have that one more lecture at the end of this week, just to show another example, a more interesting example maybe of how an ODE might arise from some mathematical modeling situation. And we might look at one or two other further properties of the transform as well. Okay. The question I'm going to show you, I can switch that in now, is an old one. It goes back to 2004, so you won't have this on your, you won't have access to this on Moodle. It's kind of too old. It's disappeared from the system. But it's a nice example of an ODE problem using the Heaviside step functions. Okay. So it's still good. It's still some good revision for us. Okay, so let's look at what this question is giving us. So it's question 3 from 2004. So it presents us with this function f of t. F of t, you can see, is a piecewise linear function. It's made up of two straight line parts. And it's asking us to show or show how this function f can be written in this form. Now we'll discover this correct form in a moment, but it's asking for it to be converted into a combination of Heavisides. Okay, combination of Heavisides. And then to take this result to go on and solve this differential equation, d2y dt squared plus 9y equals 27 f of t, where f is this function displayed in the graph up here. Okay. So it wants us to solve this differential equation. So it's the second derivative of y plus 9y equals 27 f of t, where f is this function illustrated in the graph here, subject to the initial conditions that y, the first derivative of y, and y itself, they're both 0 at t equals 0. So you've got these zero initial conditions. Okay, so before you dive into solving the differential equation, the question asks us to express this function, which we can just see graphically represented there, to express it as a combination of Heavisides. Okay, so I'll put this function down here. Sketch the graph of this here. So this is our function f, and the relevant points here are 2 and 4. So 2 is the height reached by the function f, and the location 2 on the t-axis is where it converts from being one line to the other one. Okay, so what we have here is our function t. So it's these two straight lines. It's equal to t when t is between 0 and 2. Okay, because this part here, the straight line from the origin up to the point 2, 2, that's simply the straight line of 45 degrees. That's simply t. And then the second half between 2 and 4, between 2 and 4, it's on this line here. Now this is the line of, again, a 45-degree line, but this time with negative slope. It's going to be something minus t, and the something minus t would have to be 4. Yes, 4 is the intercept. And this function is equal to 0 otherwise. Okay. So everywhere outside of this picture, the function is 0. Okay, so what we're going to use here, we're going to use the idea, or use the idea of a difference of Heavisides, h of t minus a minus h of t minus b, being switched on between a and b, and switched off otherwise. Just to remind you, if you've got any two numbers and you want a function or a signal that's switched on equal to 1 between those limits a and b, switched off, i.e. equal to 0 at every other position, then it's this difference of Heavisides, h of t minus b. So we can write f. We can write f as f of t. So it's going to be t times the difference of Heavisides that represents something switched on between 0 and 2. So that is h of t minus 0, if you like, because we're switching it on at 0, minus h of t minus 2. Then we go plus the other function, I'll write it down here, which is minus t plus 4 minus t, so written it up there. And this is multiplied by the difference of heavy sides, which represents the signal switched on between 2 and 4. Okay, so then the only thing to do would just be to tidy this up now, because there's heavy side h of t minus 2 appearing in a couple of places. So we should tidy that up. So we've got t times h of t. So what have we got multiplying h of t minus 2? Well, we've got minus t and then minus t plus 4. So in total, that's minus 2t plus 4. But a nice way to write that would be minus 2 times t minus 2 times the heavy side t minus 2. So we take out that factor of minus 2 out of the coefficient of h of t minus 2 here. And then we get this nice expression where you can see the function multiplying the heavy side is itself a function expressed at the same shifted argument, the same t minus 2 term there as is in the argument to the heavy side. And then what have we got multiplying h of t minus 4? Well, we've just got plus t minus 4 times h of t minus 4. Okay, so this is the form that was printed in the question that it was asking us to establish for f of t. So we didn't really need to be given it in the question. Kind of pointed us in the right direction. And the reason we get the functions, so f is this function and it's appearing in the differential equation up here that we have to solve. So in the first step to solve that, we'll have to take the transform of the whole equation. So we'll need to be able to write down the transform of the function f of t. And because it's got heavy sides in there, we want to get it into this standard form. So we see it as a function of t times some heavy side, but the function of t, which is in front of the heavy side, is evaluated at exactly the same argument as its associated heavy side function. So these three expressions here are all set up now for applying this result from the table of Laplace transforms, which is the theorem we proved about how transforms of an arbitrary function times a heavy side, how they behave. Okay, but the products need to be set up like this: that you have a heavy side at h of t minus a evaluated at that same argument, f of t minus a. So actually, we can actually write this as the function g of t times h of t minus 2 times g of t minus 2 times h of t minus 2 plus g of t minus 4 times h of t minus 4. See, it's the same function g that's applying in each case. G of t, or minus 2 times g of t minus 2 plus g of t minus 4. So it's just a simple function g, which is defined by g of t equals t. Where g is the function defined by g of t equals t. Okay? So that's what's going on here in these three different terms of that. Okay, so the transform of f is this function capital F of s which is well, we're going to be applying multiple cases of that result about how to transform this function times the Heaviside. So we'll get see this Heaviside here. See the Heaviside h of t. Really, we can think of that as just the function g of t. I mean, with all of these things here, the variable t begins at 0 and goes on to infinity. And so the Heaviside step function h of t is the one that switches on at t equals 0 anyway. So that Heaviside may as well not be there. So the transform of this first term is 1 over s squared. Then we've minus 2 times, and now we have the exponential e to the minus 2s times 1 over s squared again. So it's e to the minus 2s. So this minus 2 here is the same as this minus 2. Okay, when you look at the formula on the table, this constant 2 out the front is still there. This minus 2 and this exponential here is this minus 2. Then we got 1 over s squared, which is the transform of this function g, which is being applied there. And then for the third term, we have plus e to the minus 4s times 1 over s squared. Again, this minus 4 is this minus 4 there in the exponential. So what we used there was we used linearity. And we're always using the linearity of the transform everywhere. When we take a transform of a function defined as a sum of many terms and just take the transform of each individual one. But we're actually using linearity. And the transform of things like g to the t minus a, h of t minus a, that's from the table. So we've kind of got a good handle on our function f now. We have it expressed in Heavisides, and that has enabled us to find its Laplace transform. And so since that function f is the one appearing in the ODE, we now have all that we need to go ahead and start to transform the ODE and get to the solution of it. Okay. So any questions just on that up to now before we dive into the ODE? So any clarification I can give? Okay. So let's do it. So we will write y bar for the Laplace transform of the original function y of t. So we don't know what y is. We're trying to find it. We're trying to solve the ODE. So we should write y bar to represent the Laplace transform of this. And now take the transform of the whole ODE. And what will we get here? Well, you have to look at the ODE. So the ODE is y double prime, second derivative of y plus 9 times y equals 27 times the function f of t. So transforming the second derivative of y, we get s squared times y bar minus the first derivative at 0, sorry, minus s times the first derivative at 0 minus y at 0. Then we've got 9 times y bar, that's transforming function y, and then 27 times the transform of f, which I could write as 27 over s squared. I could express capital F by taking out all those s squareds, and that's multiplying into then 1 minus 2 times e to the minus 2s plus e to the minus 4s. Okay, now, so that's the completion of the first stage, transforming the whole ODE. The second stage was to bring in the initial conditions that we were given. So that means substituting in for these two constants here, the values given by the question. And the question gave us those as 0. So this implies I'm actually looking at s squared plus 9 times y bar equals this right-hand side. So that's after initial conditions. So now this equation only has the unknown function y bar in it, plus some algebraic terms in terms of s and some exponentials of s. So we can go ahead and solve this now for y bar. So that won't be too taxing. We just divide both sides by s squared plus 9. And then we still got this combination of exponentials here. So in principle now we only have to take the inverse transform to solve this. Okay? So when we take the inverse transform of this equation, we'll recover the original function y of t on the left, and whatever the inverse transform of this large function is here, that will be the solution y of t. Okay, but we have to prepare this right-hand side before we can take the inverse transform of it. Now we see a bunch of exponentials here. Okay, the constant 1, then an exponential e to the minus 2s, and then e to the minus 4s. And they're multiplying this function of s, this 27 over s squared times s squared plus 9. So what we'll use to transform the right-hand side is we'll use a few applications of this result about the transform of something times a heavy side. Okay, because what we're seeing on the right-hand side there is some exponential times the transform of some function. So this f bar of s here is that 27 over s squared times s squared plus 9 that's appearing here. And this is multiplied by, okay, well, constant 1 here, but those other exponentials. So for transforming the fraction times this exponential and the fraction times the last exponential, we'll need to use that result again. So we need to be able, now part of using that result is you need this function f of, well, the f bar here, you need the original function f from that, the inverse transform of that function f bar. And using that inverse transform, you then evaluate that at the appropriate shifted argument t minus a corresponding to that parameter up in the exponential. Okay. So what we'll need here is we'll need oh dear, I've just made a, that's okay, let's just go. Okay, so we'll need a partial fraction expansion of this, okay, because we'll need to be able to clearly identify the inverse transform of this. Okay. So we'll need the partial fraction expansion of 27 over s squared times s squared plus 9. Now we won't, okay, having these quadratic factors here potentially this could have quite a long partial fraction expansion. But if we could know it just to this level, something over s squared and something over s squared plus 9, that would be sufficient, okay? Because these types of functions, constant over s squared and the constant over s squared plus 9, those kind of functions are on our table of Laplace transforms. Aren't they? Yeah. So if we could know it to that level, that would be sufficient. And because this is s squared and this is s squared plus 9, and we just need to obtain a 27, you can see that what we need is we need to have a 3 over s squared. Because when that's collapsed together again to a common denominator, you'll have your 3 times 9, which will give you your 27. Of course, you'll also get a 3 times s squared, so we want to get rid of that, because there is no s squared in the numerator over there. So we just have a minus 3 on this one. So minus 3 over s squared plus 9. Okay, so it's 3 and 3 are those two coefficients there. So we can write h of s to be this. Sorry, let's write that. H bar of s to be this 3 over s squared minus 3 over s squared plus 9. Okay, because this is the function h bar of s, which is multiplied by, well, it's sitting here in this constant, and it's multiplied by those exponentials. So we'll take its inverse transform. The inverse transform of this h bar of s, well, the inverse transform of 3 over s squared is 3 times t. And the inverse transform of 3 over s squared plus 9, so you look down your table, and constant over s squared plus positive constant, that's a sine. Okay? If you look at the entry for sine omega t on your table of Laplace transforms, where omega is 3, that's exactly what we're looking at there. So this would be minus the sine of 3 times t. Okay, so this is this function h bar of s, which is this term here, multiplying those exponentials. So taking the inverse transform of y bar now, we get y of t equal to h of t. Okay, so you got the first term is just the constant 1 times this, so times h bar of s. So you take the inverse transform, you're going to get h of t. We're going to get minus 2 times h evaluated at t minus 2 times the heavy side of t minus 2. So that's applying that result about transforms of heavy sides from the table to our function h of s times exponential e to the minus 2s. We get this minus 2 constant, so we're using linearity, so that's still out there. And then it's h evaluated at t minus 2 times the x times the heavy side, large h evaluated at t minus 2. And then there's this third term, which is our little h evaluated at t minus 4 times the heavy side evaluated at t minus 4s also. Okay, so where h of t is this expression here. So i.e. you get y of t being 3t minus sine of 3t minus 2 times 3 of t minus 6. Because 3 times t, but this time you're evaluating it at t minus 2, so it's 3t minus 6. Minus the sine of 3 times t, so again 3t minus 6. And that's all multiplied by heavy side h of t minus 2. And then lastly, you have the corresponding thing, but this time taking place at t minus 4. So 3t minus 12. minus the sine of 3t minus 12 again, and this time multiplied by the heavy side h of t minus 4. Okay, so you can see how our solution y is made up of this expression, this kind of t and sine of 3t, but with various copies of it, evaluated at various shifted arguments that get switched on at various times. So t equals 0, t equals 2, and t equals 4. So that would be more or less tidied up our final solution for that ODE. Okay, I think I'll leave it there. Or is there any questions about that? Any clarification I could provide? Okay, so just one more lecture on Laplace transforms to come on Friday. Go through another example, but a more meaningful example, one with kind of, or will show the context where it's come from as well. Maybe one or two final properties of the transform we'll look through as well. Okay. Just let me do this.